Good morning, everyone. We are pleased to have Professor Ethan Fang to give a virtual talk. Ethan is Associate Professor of Biostatistics and Bioinformatics at Duke. He's also affiliated with the Decision Science Group at the Fuqua School of Business. He works on various problems, especially on different data science problems from both computational and the theoretical perspectives. Before joining Duke, he was assistant professor of statistics at Penn State University. He got a PhD in operation research and financial engineering from Princeton University, working with professors Han Liu and Bob Vanderbilt. He got a bachelor degree in math from National University of Singapore, working with Professor Kintran Tuo. Currently, he is serving as associate editor for two top-tier journals, which are Atlas of Statistics and Operation Research. So let's welcome Professor Ethan Fang.
Yeah, thanks, Professor Lu, for the invitation and the very generous introduction. So first, I do want to apologize. So due to some family responsibility, so I could not travel to Minneapolis, though I do want to travel and meet friends there. So, and the title of my talk is Estimation and Inference for Assortment Optimization. So it's divided into two parts. In the first part, I will talk about the estimation problem. And in the second part, I will talk about the inference. So, let me start with the first part. So this is based on the paper PASTA, Pessimistic Assortment Optimization. The short version has been published at ICML, and the longer version is in submission at Econometrica. So first, let me introduce my fantastic collaborators, including the fantastic third-year PhD student at our ECE department, Jun Chen, and Wei Bin, who is an assistant professor at Purdue, and Zhen Ling, so assistant professor at George Washington. So and Kong, who also graduated from NUS and is currently at Miami. So he moved from Michigan IOE recently. So and my colleague Vahid Taroki. So let me start with the background and talk about a toy example to motivate the work. So suppose that I go to a car dealer and when I need to buy a new car, but if the car dealer only offer me two very luxury brands, such as Ferrari or Porsche, so as someone works in academia, so there is no way for me to afford either of these two brands, even though admittedly all my classmates who didn't go to academia now can easily afford either of them. So, but instead, if the car dealer offer me some more choices, like those more affordable brands like Toyota or Honda or even Tesla, so then it becomes feasible for me. So what this example really shows is that, so what we get offered actually changes our behavior. So customers, when we go to either a grocery store, supermarket, or by a car dealer, or even we go to Amazon and search some keywords of our interest, what we got offered actually impact our choices. So such choices is extremely important in economics and is even beyond the application I talked about. So, so in early 1970s, so this famous economist, Daniel McFadden, so proposed the choice model, which is, I will talk about in details later, the multinomial logistic choice model. So, so in his work, it's actually more broad because, from his perspective, it's used to model behavior economics, to model the choices people make in different scenarios. So not just buying products and in making other saving, purchasing, and other choices. It can also be broadly applied for other choices, including government applications. And it becomes fundamental in behavior economics, and he was awarded the Nobel Memorial Prize in Economics in 2000. So Then from our perspective, so let me talk about the problem, the assortment optimization, which is an extremely important problem in operations research. So from the seller's perspective, the seller can, there are n items the seller has, and the seller needs to decide which of them should be offered to the customer. So here, so we assume that we have a capital N items that we can offer to the customer. And each item, we assume it has some feature in the D-dimensional space. So the seller's goal is to find an assortment to decide which, for example, suppose we are a car dealer, we have 5 choices of the brands. We need to decide which of these 5 should be offered to the customers. And the goal here is to maximize the potential expected revenue. So that's the problem. So, and this assortment optimization problem has been widely studied in operations research literature. So most of the work follows the seminal multinomial logit model, which was proposed by McFadden in 1970s. So, but this model was is for a more broader application, not just for assortment optimization. So first, this model was adopted by Taluri and Van Rysing in 2004. So to me, this is a seminal paper. So use the MNL model to model the assortment optimization, and it becomes very popular in operations research community. So first, it's a combinatorial optimization problem, and it has different variants. So they were studied broadly from algorithmic and modeling perspectives in operations research. So in the past few years, so data-driven optimization becomes much more popular in operations research. And data-driven assortment optimization has been widely studied in operations research community, and a lot of work has been done by my co-author. For the other work I will present in the second half of today's talk, Xi Chen and my other collaborator, Yining Wang, now at UT Dallas. So, but most of the work is to study the online version of the assortment optimization. So it's called dynamic assortment optimization in operations research literature. So basically the problem is formulated as a bandit problem, and people say how we can iteratively update the assortment to be offered in the hope that we can identify the optimal assortment later. So, but in our work, we consider the offline setting, means that given the existing data, so we want to mine from the large data set to find the optimal assortment. So, and I should mention that offline assortment optimization is largely unexplored in operations research. So just to be more specific, say what do I mean by online and offline settings? In online setting, it's adaptive. So the seller can trial and make error and try to improve. So for example, so in the first iteration, say in this toy example, so because usually car dealer only carry one brand, just take it for illustration purpose. So for example, in the first iteration for the first customer, the car dealer offer only 2 of those 5 brands, including Lexus and Toyota. And the seller observes that the customer makes the purchase of the Lexus, but the customer didn't choose Toyota. So in the second iteration, what the seller could do is to keep Lexus, which was bought by the first customer, and include 2 other brands, but not including Toyota because it was not chosen by the first customer. So the seller can choose Ferrari and Rolls-Royce for the customer, and the seller observes the customer's other purchase and can iteratively update the assortment to be offered to the customer. So here, to me, this such online assortment optimization is only feasible in the online, for internet sellers. This is because if the seller changes what to be offered to the customer, there is some cost for the experiment. So especially, so if in the car selling industry, it's impossible for the dealer to change what to be offered in a short period of time. So, but in the offline setting is that we mine the historical data. So because of, given the past purchases data, so we have a large data set of in the past, what is offered to the customer and what is the customer chooses. So, and I should mention that, so we can also, in this work, we observe that the no purchase behavior. So means that if we offer customer some choices, but the customer didn't make a choice, we record such no purchase behavior. But in literature, there are works considering such no purchase cannot be observed, which is realistic for some settings. So so just the offline set, the main difference between online and offline setting is that in online setting, we can change the offering set iteratively by adaptive to what customers' behaviors. But in offline setting, we only have the historical data. So, and we cannot make any experiment. So, but to me, offline setting is more realistic because for many sellers, they cannot afford to do the experiment to iteratively update the offering set because it's unrealistic to change the offering set from day to day. And also, during the experiment, because it's to ensure the full exploration, they will make mistakes. They will make mistakes by offering suboptimal assortment that will incur revenue loss in practice. So let's talk about our problem formulation. So this is the causal inference model for the problem. So PIS is the policy of the seller to decide which set of products to be offered to the customer. Then, based on the offering set, the customer may make a choice. This action is to either not buy or not to buy. And if the customer buys one of the products, so the customer needs to choose from the offering set. So here, this customer's behavior, the action, is modeled by is conditioning on the offering set S, and we have a model. We model the model is described by a parameter theta that I will talk about later. So, and after the customer makes the purchase or no purchase, then it incurs the revenue. So our goal is to maximize the expected revenue. So our goal is and to achieve the optimal revenue. Our goal is to find the optimal assortment, the set of products to be offered to the customer. So, and by definition, it's the expected revenue. It's the expected revenue. So this is the definition, the summation of the product of the corresponding revenue of the product and the conditional probability, conditioning on the model and the offering set. The customer chooses this particular product J. So this RJ is the associated revenue. So here, let me make a remark. So we assume that this revenue is known and it does not change. It does not change. But in practice, the revenue is actually random. So thinking about, we go to Amazon. So the product, the price of a certain product today is because today is actually one of the Amazon Prime Day. So many products are on sale, on discount. So the corresponding revenue is lower than it in the previous days. But to simplify our discussion, we assume that the revenue is a constant for each product. So, but our model can be adaptive to such random revenue. So but it's more tedious. So we only present the constant revenue model here. So, and what we have is the offline data set, the historical data set. So in the past, for each sample, we have what is offered to the customer. This SI is the offering set to the ICE customer and the customer's behavior, AI. So again, so this is what item the customer I bought, or it can be the no purchase behavior and the corresponding incurred revenue. So, and we assume they follow the follow distribution jointly of what's offered by the seller and the corresponding choice model of the customer. So here, note that I haven't specified the choice model. So, so the framework actually works for all choice model, as long as it can be parameterized by some finite dimensional parameter theta here. So this is the model. So, and to say why this problem is very challenging. So first, it has the combinatorial structure. So let me elaborate this. So suppose, so we can, for each possible offering set, we can do experiment and collect enough data. We can then accurately estimate the corresponding potential revenue for the corresponding offering set. But this is not possible because the seller cannot just do experiment and not worry about the revenue not worry about the corresponding revenue, because if we want to say, for example, we want to collect the data for a very bad offering set. So this will incur a lot of potential revenue loss. So, and in the historical data, only a few assortment is observed. So in theory, there are a total n possible items. So in total, there are 2 to the power of n possible combinations of the assortment. So, but we may not have an observation of all of them. We may only have the observation for a few of them. So there is insufficient data coverage problem. We cannot apply the simple statistics to calculate what's the corresponding average revenue for each assortment. So for some assortment, we have more samples, but for some, we may not have accurate estimation because lack of data. So here, let me talk about the graph. Here, each dot represents the underlying true potential expected revenue. So it's Oracle data that we do not have access to. But after having some data for the corresponding assortment that we have data, we can build a confidence interval of them. So for example, for this assortment, we may have fewer samples, so we have a wider confidence interval. But for this, we may have more sample, we have a more accurate estimation. This translates to a narrower confidence interval. So this is what the figure is showing. So the x-axis, so this with a slight abuse of the figure, so it corresponds to different assortment. It doesn't mean that something is increasing. Okay. So by the way, I should say, feel free to stop me if there is any question. So our goal is to find an computationally efficient and theoretically justified offline algorithm to estimate the optimal assortment set without unrealistic assumptions on the offline dataset. So let me just give you an example of one unrealistic assumption is that suppose we have enough data from each assortment, then we can easily identify the optimal assortment. But this is a totally unrealistic assumption. So we want to get rid of that. So first, before talking about our algorithm, so let me talk about how do we get the intuition. So, and because this is to choose one of the best assortment, as I talked about earlier, in the online assortment optimization literature, which is widely started. So people use the spirit of optimism to identify the optimal assortment. So what do we mean by optimism? And this spirit is for more efficient exploration. So such as follow one with the upper confidence band. So for example, so suppose in the online setting, after a few iterations, suppose this is what we have. What do we mean is that for each of these assortments that we have observations, for each of them, we have a confidence interval. And for this one, it has a very wide confidence interval, potentially because that we have fewer samples for it. But for this one, we we have a narrower confidence interval because potentially we have more samples for it. So, and in the next iteration, which one we should choose? So, following the spirit of optimism, this one is the alternative we should choose because it has the highest upper confidence band. This is by following the seminal work of UCB in bandit literature. So the reason we, roughly speaking, the reason we choose this one is that first, it has the highest upper confidence band, meaning it has a great potential to achieve a higher maximum revenue among all the assortment we have if we do more experiment with it. Because for this one, so we have a pretty good understanding of it. Even we do more experiment, so the best it can achieve is the upper confidence band here, so which is not something significant. But this one, without access for the oracle information of the true value, it's still that if we try it, it may improve the optimal value to this point. So, and that's why following the spirit of optimism, we want to do more experiment on this. And thinking about it is online, say after we try it for another 5 iterations, so the confidence interval will become narrower and eventually converge to the true value. So, and even if we make mistakes, it's fine. So it's fine. So we will realize it in a few iterations. So, but unfortunately, we have offline data. This spirit won't work. This spirit won't work. For example, if this is again, the black dots are the true expected value. So following the optimism spirit, we choose this one. And because we are doing offline, we cannot do more experiment. Then this is clearly a suboptimal choice, suboptimal assortment. So in the offline learning, inspired by the work in offline reinforcement learning, so we propose that we should follow the spirit of pessimism. So what do we mean here? So first, we note that we may not necessarily estimate the value of every assortment accurately, as long as suboptimal assortment can be safely ruled out during our optimization. So in particular, for this one, instead of looking first in the bandit literature, let me talk about the pessimism spirit in bandit or reinforcement learning literature, is that instead of looking at the upper confidence band like this one here, we look at the lower confidence band and see which one has the lower confidence band. So just come back in here. This one has the highest upper confidence band just because that we do not have enough sample to build an accurate estimation of the confidence interval. So while it has the highest upper confidence band, because the confidence interval is wide, its lower confidence band is also low. So it's also low. So the upper confidence band, the highest upper confidence band comes with a price with a lower confidence band. So if we look, so in the offline setting, so in the bandit literature, so people realize that we can find the one with the highest lower confidence band. So to find the worst case, to pick the assortment. So, but this is not directly we cannot directly apply this spirit to solve our problem because our problem is a little bit more challenging. So, but what we realize is that by following this pessimism, we can safely rule out some choices. For example, if we require that the lower confidence band to be lower bounded by what I put here, by this much, we can rule out these 4 choices in the red region. So we only need to worry about these 3, which may greatly simplifies the problem. So this is before talking about the algorithm model, let me first talk about some notations. So this is the value function of what we can achieve. So given a particular assortment, if the true parameter of the choice model is described by this theta, this is our value of this corresponding choice. Corresponding choice S is just equals the expected revenue. So if we take the theta as theta star, the true parameter, then the corresponding value of the assortment S is the true expected revenue of the corresponding assortment. So, and because this theta star is the true parameter, which in practice is unknown, so we need to estimate it. So and then we'll talk about later. If for most of the choice model, we can estimate this parameter by different approach, like the maximum likelihood approach. So yeah, and we can plug in the estimator and have an estimate of the true value function, which we call the maximum likelihood estimate. So our goal is to minimize the regret. So what do we mean by regret? Is the difference between what we achieve and what is optimal. So for an estimator of the assortment S hat, so its regret is by plugging in the true parameter theta star, we look at the difference between what the optimal assortment could achieve and what we actually achieve in expectation. This is the regret. So we want to propose an algorithm that could achieve the optimal regret. So, and just to talk about a little bit more details. So the maximum likelihood estimation is following the model of the choice model, and given the past data, we can have an estimator of the choice model theta. So the customer's behavior is modeled by a model, so which I haven't specified. So and the corresponding parameter can be estimated by the theta. So, and the naive approach is to do a plug-in estimator of the value function. What it means is that we get the estimator of the choice model's parameter theta hat here. We just plug it in, and we can calculate the corresponding value function. So we can optimize it. So this is because if the choice model is specified, so earlier works in operations research tells us we can easily, in polynomial time, get a corresponding optimal assortment, which because it's not our contribution. So let me not talk about it. So, but unfortunately, this approach is provably suboptimal. So we can show there is a gap between what this approach can achieve and what the lower bound is. So this is suboptimal. So instead, following the spirit of pessimism, so we build a confidence set. What we do is that we build this set omega n specified by alpha n. So alpha n for now, I just say it goes to 0 as sample size goes to infinity. N is the sample size. So and what this set is that just around the maximum likelihood estimator of the choice model. So we want to consider all theta that the corresponding maximum likelihood function value is not alpha n different from it. So because this theta, this maximum likelihood estimator minimizes the corresponding maximum likelihood function. So what this theta is doing is to say, instead of just looking at the maximum likelihood estimator, we look at a neighborhood of it. So as long as the corresponding maximum likelihood function value is not alpha n worse than the optimal value, we keep it in consideration. So this is the corresponding we call pessimistic set. So and so we propose, instead of using the looking at the maximum the naive approach, the plug-in estimator, we look at the theta that we look at the theta within this set. So and we find the assortment that maximizes the worst theta for the corresponding assortment. So this is like a robust optimization problem. So we maximize the assortment choice, maximize the corresponding function value for the worst theta within this set. This is what we do. We call this pessimistic assortment optimization, short for PASTA. Okay, this is what we do. So, and we show that this approach indeed can bring us theoretical guarantees for the regret. So, and here, let me just specify this number. This is some technical detail, but it's important to specify this number to show the regret. So let this RS star be the revenue of the most profitable item in the optimal assortment. So this RS star is the item in the unknown optimal assortment with the highest revenue within the set. So, and we let this CS star be the inverse of the corresponding probability that the optimal assortment is chosen in the offline data set. So, and to guarantee the theoretical result, we still have some assumption, but it's more realistic. So we need to assume that the probability the optimal assortment is observed in the offline data set. Means that in the offline data set, we do have the opportunity to observe the optimal assortment with certain positive probability. And suppose that this pessimistic set indeed covers the true theta star, Then, and some mild technical assumptions that I do not go into the details here, then we can show with a high probability, or I should say with the probability goes to 1 if the sample as the sample size goes to infinity, we have that the regret diminishes at a rate of 2 square root 2 alpha n times this CS star, this constant. And it's also related to the most profitable item in the optimal assortment's revenue. This is the regret. So here, let me mention that this doesn't look like it goes to 0, but this holds for any choice model. So I'm not specifying the choice model yet. So, and we can show that for any choice model, this alpha n, to guarantee that this set covers the true theta star, this alpha n goes to 0. So this regret indeed goes to 0. So, and I will talk about the specific example of under the MNL model in the next few slides. So the most importantly, so as I talked about earlier, the main challenge of this problem is that we have insufficient data coverage. We cannot observe all the possible assortment in the offline data set. So, but we only to identify, to have the regret goes to 0, we only require that we have certain probability of observing the optimal assortment. So to me, this is a mild assumption. So because in order to have the regret goes to 0, if we have never observed the optimal assortment in the data set, there is no hope. You just like when you do bandit problem, if you have never tried certain choices, there is no choice, there is no probability we will pick such choice as the outcome. So this is the main theoretical results, general theoretical result. So then let me talk about a specific application. So the application is under the MNL model, the multinomial logit model. So, and this is the original model proposed by McFadden, which later makes him a Nobel laureate in 2000. So here we assume that the parameter space is compact. So, and this can be easily relaxed. Then for some parameter in the set, so the choice model can be described by this logistic model. So just for the particular choice A, it's just the exponential of the product of the true parameter and the feature of the choice. So in our application, so the A is, you can think about it as the feature vector of the corresponding product. So the probability given an assortment that the customer will choose this product A is the exponential of the inner product of the feature vector of the product and the choice model's parameter theta over 1. This 1 is true first that makes the model identifiable. And also this model's the no purchase behavior, plus the summation of the exponential of all the choices, the inner product of all choices in the model and the true parameter. So this is the MNL model. So, and it's widely used in operations research literature. So what we show is that for the MNL model, we can actually have a closed form solution to choose the alpha n, which I do not present the detail here. Just the key message is that this alpha n can be chosen efficiently to satisfy our requirement, and assuming some other technical assumptions which are mild. So, and by our proposed pasta algorithm. So, and alpha n chosen at this order. So d log n over n, d is the dimension of theta, dimension of the feature vector of the product, n is the sample size we have in the data set. Then with probability goes to 1, we have that the regret converges to 0 at the rate of square root d times log n over n. So this is the regret. So, and we show that. So we can show whether to say that whether this regret is optimal or not. So what we show is that the regret is actually lower bounded from the minimax perspective by the constant times the square root minimum over d, and n. N is the total number of items, total choices of the items we have to be offered to the customer over n here. So, and we say that this this bound matches the minimax lower bound up to a log n factor. So I don't think by the current technical framework this log n is removable, but it's close to the optimal. So, and this is for the under result for the MNL model. So I should mention that this is result is included in our ICML publication, but in the longer versions that in submission, so we show that for any choice model, as long as it's a parametric model, so we can find an alpha n that guarantees the near optimal regret. By near optimal, I mean there may be some log factor. So, but the alpha n cannot be chosen in a closed form. It has to be the confidence interval. Essentially, the this pessimistic set has to be built by some bootstrap approach, which is quite technical. That I skip the details here. So, and so just to talk about the algorithm. So, and we have an efficient algorithm in the sense that it can be implemented efficiently to solve the problem and gives nice empirical results. Is that in each iteration, so given the corresponding assortment, given an assortment, we can find the corresponding theta, because we are solving a max-min problem. Then, given the new theta, we can calculate as a corresponding assortment. So, so I should admit there is still a gap theoretically. So we cannot prove that this algorithm actually solves robust optimization here. So if any of the audience has because we are all of the co-authors for this paper are not experts in robust optimization. So, but if any audience has any suggestion or pointer for some literature, we would greatly appreciate that. So, but however, the algorithm can be implemented efficiently. It's because, so given an assortment, the theta, calculating the theta is a continuous optimization problem, which can be calculated very efficiently. And given an assortment, given a theta, the corresponding assortment can also be calculated efficiently. So by earlier work in operations research, though it's combinatorial, it admits linear programming representation. Okay. So this is just some simulation result, because this again, this offline assortment optimization has never been studied in literature as far as we know. So so there is not so many benchmark to be compared. So what we compare is what we do with the plugin approach, and we show that comparing with the plugin approach, so we achieve better regret and better accuracy. So this better accuracy means that in a large number of trials, experiment, what's the percentage that we actually achieve the optimal assortment. So, and say that in both cases, pasta beats the plugin approach. Okay. So this is for the first part. If there is no question, so I go to the second part for the combinatorial inference for the optimal assortment. So how much time? I have about 10 minutes. Let me briefly talk about it. So the reason I briefly talk about it is that this is a great work to me. So, and is mainly carried by my postdoc, Shu Tinshen, who is currently at Duke. She is jointly advised by me and my colleague Alex Belloni at Fuqua. So she is on the market this year. So, so not to steal his credit, I will only briefly talk about the second part. And it's also in collaboration with Xi Chen at NYU Stern and my former classmate at Princeton, Junwei Lu, so who is now an assistant professor at Harvard Biostatistics. Okay, so the motivation of this work is to considering inference problem for the assortment. So, here, so for assortment optimization problem, so we have talked about the estimation of the optimal assortment. So, and the extensive algorithm has been developed to obtain the optimal assortment under different scenarios. But to date, to the best of my knowledge, there is no uncertainty quantification of the optimal assortment. And it's important in practice. This is because given different data set, we may get different estimators for the optimal assortment. And it's important to do the uncertainty quantification to give the full picture for the decision maker and to make the results more producible. So, so our goal is to have a general approach to do general combinatorial inference on the optimal assortment with the desired uncertainty quantification. So let me talk about the inferential problems we are interested for this problem. Is quite different from the traditional inference in statistics. So for example, so for a particular product of interest, we want to test whether this item should be in the optimal assortment or not. And a second example is for a given category of products, such as non-alcohol beverage. So, and a given percentage, we want to test, say, for example, non-alcohol beverage offerings in the assortment should be greater than 50% or not in the optimal assortment in the beverage. So, or it can test some other interesting problem. Say, if there should be more beverage to be offered in the optimal assortment than electronic devices. So you say that this is quite a different inference problem, hypothesis testing problem than the hypothesis testing problems in the statistics textbook. So in statistics, usually what we test is to infer, construct a confidence interval for a parameter like theta here. But here, you say that if we get a confidence interval for the theta, this doesn't directly help us make decisions. What we can do here is to test, to say if this item should be really included in the optimal assortment that will help the decision maker to make better decisions. So this is the general framework. The hypothesis S is the set of all possible offering set. and we want to test if the optimal assortment, this S star, is included in a set, in a subset of all possible offering set. For example, this S now can be all the offering set that includes a certain product, say Coca-Cola. So, and we test if the optimal assortment is within it. If it is within it, we can say that the corresponding item should be included in the optimal assortment. So here, we consider a simplified setting. So in the previous estimation problem, we consider the case that we have a feature vector for each product. But here, just for ease of presentation, so this can be easily generalized to the case when each item has an associated product. We assume that there is no feature vector, but just an underlying latent parameter u here to describe the choice model. Essentially, this u is the exponential of the product of the feature vector and the true parameter. So the optimal assortment is again to maximize the corresponding expected revenue. So, and the key observation we have is that the story is that we independently discovered this key observation, but later we realized it was studied in the Talluri and by Talluri and Van Rising in 2004. So we shouldn't take credit, but this is the key observation that makes the inferential framework that would work. So here we define a marginal revenue gap. Basically, this is the change of adding one more product ordered by the revenue to the offering set. So, and we observe that this delta k is non-decreasing, or is increasing. And finding the optimal assortment. So we consider the simplified case. There is no constraint on the offering set. So we want to find the largest k such that the corresponding marginal revenue is still negative. If it's positive, means that we shouldn't include this product. So, and this observation help us to change the inference, to convert the inference problem on the optimal assortment, which is a combinatorial problem, which is very difficult to model, to inference on this k star, this integer, which is a much simpler problem from the statistical perspective. So, and all we should say, this becomes a sign change point detection problem on the marginal revenue gap. So when it changes from negative to positive, then we identify the optimal assortment. So, and we can infer whatever structures of our interest of the assortment to infer the k star here, this sign change point. So, and so just to specify our model, so for this inference problem, so unlike the previous one, as I said, it can be generalized to all possible choice models. But for this problem, we can only do the inference under the MNL model. So the choice model is based on the MNL model. So, and we assume we have samples from the optimal assortment uniformly, but this can be relaxed. This assumption can be relaxed, and then we have that we assume that for each possible assortment we have L samples of it. So, and we agree that this is a relatively strong assumption, but it can be relaxed to that each possible assortment has a certain probability, non-negative positive probability to be sampled. So, and then we can estimate the parameter by the, again, log likelihood by minimize the negative log likelihood function and get an estimator of the parameter of the MNL model. So, and because the MNL model is quite irregular. It has non-positive eigenvalue for the Hessian matrix and makes the inference problem quite challenging. So we are following the seminal work of debiased inference to propose first and debiased inference approach to infer the parameter of the choice model. What we have is that this eta hat d is a valid. It follows asymptotically, follows a normal distribution around the true parameter. So then we have a valid inference for the parameter of the choice model. So, but as I talked about earlier, finding a valid inference for the parameter of the choice model doesn't help us make decisions. We still want to infer the structure of the optimal assortment set. So, but we have that by looking at by inferring certain set of the optimal assortment, it can be converted to the optimal optimal inference for number k star, the sign change point. So it becomes a sign change point detection of the marginal revenue gap. So our goal is to establish a confidence interval for the this sign change point. So and this becomes first by the debiasing approach, where we can actually plug in the confidence interval for the parameters to get a valid inference for the marginal revenue gap. So and this can help us infer the whether this item I should be included in the optimal assortment. So, but for general inference problem, like to test whether there should be more beverage than alcohol, non-alcoholic beverage than alcohol in the offering set, we need stronger results. We need a uniform form confidence interval for the revenue gap instead of just one. So, and we need to infer this maximal statistics, which is quite challenging. So, and this is very technical. Let me not go into the details of it. So, but we can use a Gaussian multiplier bootstrap approach to actually to construct the confidence density interval for the parameter of interest. And then we can get a valid confidence interval for the k star, the sign change point. So, and this is very technical. Let me not go into the details. The point is that this method can be carried out efficiently from the numerical point perspective. So, and then we show that by having a valid confidence interval for the sign change for the point of sign change point, so we can actually control the type 1 error rigorously for the hypothesis of our interest, which is to infer the broad class of properties of the assortment, of the optimal assortment, and we show that this is asymptotically powerful, means that if there is some signal, as sample size goes to infinity, we can detect such signal. For example, if item I should actually be included in the optimal assortment, we can detect such signal if there is enough sample, and we can show the method is minimax optimal. So, and there is another work is highly relevant, but I don't have time to present, is this work also useful for assortment optimization, is offline personalized pricing with censored demand. So let me briefly talk about what this work does. So given the products, so we talked about how do we find the optimal assortment and how do we do inference of the optimal set. So, but I haven't talked about how do we price those items. So, and the personalized pricing should really be called individualized pricing. So based on the product's feature, so we should find a way to give the optimal price of the certain product. So based on observing past offline data. So, and also, so the novelty of this work is that we consider censored demand is because, so given the past data, the sales is upper bounded by the inventory we had. So, and if the sales the demand is actually higher than the inventory we have, the observed sales is censored in the sense that we do not observe the full demand. So based on survival analysis approach and the causal inference framework, we propose a new optimal offline personalized pricing approach by considering such censored demand. So, and this work is jointly again with Zhenlin and Kong, and Kong's former student Jingwen, who actually joined Miami. I should update it this semester. Yeah. To conclude, so we proposed a pessimistic approach for estimating the optimal assortment, where we achieve the minimax regret. So, and is applicable to a broad class of choice models. So, and we proposed, I briefly talked about the new combinatorial inference approach for optimal assortment. So where we infer the structures of the optimal assortment. Yeah, the second work is under revision at operations research. All of the three works I mentioned. So we have manuscripts available online. So, and feel free to reach out if you want to have any more discussions of those works in detail. Yeah, that's all for the talk. Thank you very much.
Okay, let's thank you, Professor Fang, to give a very great talk. So any questions?
Questions? Yes, yeah.
Can you hear it?
Yes.
Yes.
Okay, so for the first part, you made the assumption that S star is in the data set, the optimal assortment.
Yeah.
So if you relax that assumption, like, and just require
Okay.
you choose the best assortment that was actually seen in the data set, can
Yes.
you get the results? Like,
Yes, this is a great question. So I should mention this in the talk. So the question is that if the optimal assortment is not observed in the set, so can the algorithm identify the best assortment in the data set? The answer is yes. So the reason we make this assumption is that we want to show the regret goes to 0. So by identifying the best assortment in the data set, which is not the optimal one, so we cannot prove the regret bound. That's the reason we impose this assumption, but this is a great point.
but if your regret is against the best data set, best thing in the data set, that the regret is measured against.
Right. The regret is measured against the optimal assortment. But I agree. So if the measurement is measured against the best one in the data set, it still goes to 0.
Thank you.
Okay, thank you.
Other questions?
No question.
Yes, go ahead.
So you know both of the work you mentioned, you based on you assume MNL model. So I just not sure why we need based on this model, and do we have any other models that we could base on? Because
Sure. So for the first one is that I mentioned is that we need to calculate this alpha n based on MNL model. We have a closed form solution for the alpha n. So this is for the first short version of the paper. In the longer version, we show that for any choice model, we can calculate this alpha n, but just not the closed form alpha n. We need some bootstrap, which is computationally more intensive to calculate the alpha n. But for the second approach, so I should mention that MNL model is essential for the development for currently. So this is because we need to have a valid inference. Here, let me go there. So yeah, valid inference for the parameter in the choice model. So and this we have by debiasing approach, we can actually infer the parameter in the MNL model. But for other choice model, this may not be the case. But as long as we can have valid inference for the choice model, the method works. Does this answer your question?
Other questions?
So yeah. So I think so for the min max problem, max min problem.
Yeah.
So what about this non con is convex concave convex or what kind of
Good question. So it's combinatorial. That's why it's difficult
combinatorial?
in the sense that this argmax is optimized over the assortment, which is combinatorial. That's why we cannot prove the algorithm converges to the optimal one.
I see. I see.
Yeah.
So what about the omega n is convex set?
Yeah, this is a convex set.
Okay.
This can be shown. It's a convex set for all the choice model we know. Yeah.
Okay. Okay.
Yeah.
Yeah. So that way you proposed some approach is not like a alternating approach. So
Yeah.
does that approach find the global optimal solution to this problem?
No, so we cannot prove it, but it works well numerically. There is still a gap. This one algorithm, we cannot show that it converges globally.
Okay, I see.
Yeah,
see.
because
Yes.
of the combinatorial structure of the problem.
Yes, it's an NP hard problem, right? I
Yeah,
think.
yeah,
Yeah.
yeah.
Okay. All right. Thank you.
Thank you.
So any more questions? All right. Okay, if you do not have questions, let's thank the speaker again.
Thank you.
Right.
Yeah.
Okay.
Thank you. I will see you later.
Okay, see you later, Ethan.
See you
Okay,
later.
thank you.
Bye.
Yeah, bye.
Bye.
Thank you, guys.
Thank you, Ju.